Okay, this video is going to cover that nth term test for divergence. This is on your page 258. If you weren't in class today and you didn't get to page 258, I'm going to go ahead and attach it as well so you can print it out and take your notes. So target students will apply the nth term test for divergence to a series using limits to infinity to determine if the series diverges. Okay, so let's kind of talk about a series. Now let's talk about the series, or actually let's start off by talking about the sequence, this a sub n equal to 2n plus 5 over 3n minus 4. Now, we talked about the sequences, and really there's only one test for sequences to determine if they converge or diverge. And that's that limit test that we started talking about on Tuesday. If we take the limit of this sequence, and we get a finite value, so a numerical value of some sort. So for instance, let me grab a pen. If we take the limit as n approaches infinity of this 2n plus 5 over this 3n minus 4. Okay. Remember, limits to infinity, we're looking for that relationship. Who's growing faster? Numerator, denominator, or are they growing at the same speed? And we look at our highest term to do that. So in our numerator, our highest term is that 2n. In our denominator, our highest term is that 3n. So really they're going at the same speed. Okay, so if that's the case, then we look at the leading coefficients. So in this case, 2 and 3. So our limit's going to actually be equal to 2 over 3. Because that 2/3 is a finite value, it is a number, we automatically know that the sequence converges. So therefore, remember 3 dots, therefore sequence converges. And it converges to that value of 2/3. Okay. Now, just because our sequence converges doesn't mean the series that is similar to that sequence is also going to converge. They will not have the same habit. The fact that we're adding the addition, that property in there, can change convergence and divergence. So just because our sequence converges doesn't necessarily mean our series is going to converge, and vice versa. If our sequence diverges, it doesn't necessarily mean that our series will diverge. Okay, so if we're thinking about the series themselves, we can't really tell. Okay, we're talking about an infinite sum here, that idea of infinity. Okay. So going on forever and ever, if we keep adding terms, is it going to come and get close to a single value, or is it going to blow up and keep getting larger and larger and larger in value? So in order to do that, we don't really have a set test for this. This is not geometric, so we can't use a geometric series test. So we look at what we call our partial sums. So I'm going to look at two very finite sums. I'm going to use some notation. Let me erase that. Make it a little bit thinner. Maybe that will help. I'm gonna not that. Ignore me while I try to figure this out. Fast forward. Maybe that will help. Okay. So if we think about that particular series, the series of the sequence we mentioned above, and we look at what we call the finite sum. So if I'm going to take a finite sum as n starts at 1, let's go ahead and start at 1. And instead of going to infinity, we're going to go to 5. Okay. We call this a partial sum, and we notate it like that. Instead of an n being there, there's going to be a 5. That tells us our end point. And we look at this 2n plus 5 over this 3n minus 4. If I was to put this in the calculator, we kind of talked about how that is in the calculator. We calculated a couple of them. If I did that, I'd wind up getting 1.4306. And I did this earlier. Okay. If you're in a class that we already did this, we probably use a different value, and that is okay. So the first 5 terms, if we add them up together, we get that approximately 1.436. So now I want to look at a higher value. So not 5, but let's go with 10 instead of 5. If we go with 10, that means we're taking the sum as n equals 1, and we're going to stop it at 10. We're not going to go to infinity of the same exact sequence. I took this, I plugged it into the calculator, and I got 6.7821. 7821. So between 5 and 10, it grew about 5 values. So it is increasing, which makes sense. We're adding positive values in there. But is it increasing enough to say that it's going to diverge? That's the question. Or is it going to start tapering off and get to a close value? And the only way we figure that out is to look at a sum with more terms. So let's look at a sum with, let's say, 100 instead of 10. I know that is really bad. So we're going to go n is equal to 1, and let's go to 100 of that same sequence. If we do that, plugged into the calculator, we wind up getting 72.8662. So now it jumped up quite a bit. Makes sense, 100 terms, that's a lot of things that we're adding together. Okay, I'm gonna go one more, because just like with sequences, sometimes we need the first 4, or we need to test 4 values to kind of see the pattern. Same thing here, I wanna go up. We're increasing our sum, or the number of terms we're summing up, to see if the pattern is gonna continue. So instead of going 100, let's say to 1,000. That means we're finding the sum, where n is equal to 1 to, not infinity, keep drawing the same thing. Please fast forward until I actually get this in. Okay, so S of 1,000, the sum of the first 1,000 terms, of the same series, or the same sequence. Okay. So if we do that, again, I plugged this in the calculator earlier, and I got 678.7698. Okay. Again, when we do this, when we find the S of 5, S of 10, S of 100, S of 1,000, what we're doing is finding the sum, the partial sum. Not the infinite sum, but a specific number of terms adding up together. And if we look at the pattern, we started out with 1, we went to 6, we went to 72, and now we're at 678. So if I add another 0, it seems like it's going to keep increasing without bound. And because of the fact that it increases without bound, we can say that the series is going to diverge, or we can predict that the series is going to diverge. So I'm going to put that in a different color. So I would say the series diverges. We're going to make that prediction right now. Diverges since the partial sums increase in value. Okay, so we're going to make that prediction. Now, the only definite way to determine whether something converges or diverges is to actually use one of our convergence tests. We spent 2 days talking about the geometric series test, so I'm going to introduce the next test, which is our nth term test for divergence. Let me get it on here. Okay. Our nth term test says if we find the limit as n approaches infinity of the sequence and it does not equal 0, that's important, that it does not equal 0, then the series, we can say that the series diverges. The nth term test is a test for divergence and divergence alone. Okay, so that's important. Please highlight that. You cannot use this test to prove convergence. If the limit of a sub n is equal to 0, the test is inconclusive. That's important, so let's write that down really quickly. Okay. If the limit as n approaches infinity of a sub n does equal 0, the test is inconclusive. And I can't express that enough. If the limit does equal 0, that doesn't mean it converges. That just means we can't prove that it diverges. We're going to have to go to something else. Please highlight that. That is an important thing to always remember. Okay, write that down and highlight that. Okay. So the nth term test for divergence only proves divergence. It does not prove convergence at all. Okay, so let's see if we can use this and prove some of our series divergent. I think I tilted it a little bit, but that's okay. Okay, so if we have the following series, we want to see if they diverge, if this test tells us that it diverges. So the first thing I want to do is actually take the limit. Remember, when we talked about proving divergence and convergence with geometric, I said we want to state the series, we want to state the conditions, and then we want to state the test that we're using once we get to our conclusion. So the first thing that we want to do is evaluate the limit, because those are the conditions. So our first thing in all of these is to just simply evaluate the limit as n approaches infinity. So for this one, the limit as n approaches infinity of n over n plus 1. Okay, again, we look at our highest terms. So our highest term is n here, our highest term is n here. And because they are the same, we look at the coefficients. So 1 over 1, which is equal to 1. Now this is not equal to 0, which means the series does diverge by the nth term test for divergence. So I want to write that. Okay. I want to write the series. This is not a known name series, so I don't need to state the name of it like I did with geometric. Okay, it's just a generic series. I would say the series diverges by the nth term test for divergence. Since, and here's my justification or my conditions. Okay, that's the proof. So I stated the series. I know I didn't name the series, but the fact that I'm talking about the series, I'm answering the question, diverges. I'm stating the test, and I'm using the conditions for the test, which are right there. Okay, so let's try another one. First thing I want to do is take the limit. It is not geometric. Sorry, my phone is going off over here. As n approaches infinity of 2n factorial, we talked about those the other day, 3n factorial minus 8. Okay, so we want to look at the biggest term. Okay, so our biggest term on top, well, there's only one term right there. our biggest term on bottom is at 3n factorial. Because they are growing at the same rate, then we look at the leading coefficients, which our leading coefficients happen to be 2/3, which is not equal to 0. Okay. So I'm going to do this a little bit shorthand. Nth term test, we've evaluated the limit, so there's our conditions right there. So now I can say, therefore, let's use our symbol. The series diverges by the nth term test. For divergence. So there we go. Okay, my conditions, which are my work right here, the fact that we're talking about the series, and then of course the fact that we've named the test. 3 things we always want to include. Okay, and the next one. First thing again, I'm going to take the limit as n approaches infinity of 1/n. Okay, so in this one, my denominator is growing really, really fast, which means my value is getting really, really small. So this is equal to 0. Because of that, we cannot determine convergence. We can't determine whether this converges or diverges because of the fact that this limit is equal to 0. And in this case, we would have to go to a new test. We would have to try a different test. But since we only know 2, we're going to stop there for this problem. We might come back to it once we get enough information. Okay. Same thing on this one. If I take the limit as n approaches infinity of 1/2n. Again, this is going to give us equal to 0. So the nth term test doesn't work here. But we have 2 tests in our toolbox now. We have the nth term test and we have the geometric series test. If I recognize that this is a geometric series, and it is because n is the exponent, so I can definitely rewrite it and rewrite it as 1/2 to the nth. Because really, I can apply that n power to 1 because 1 to any power, with the exception of infinity, is always going to be equal to 1. Okay, so I can rewrite it and it still follows the same form. Now, that means that this is our r value. So r is equal to 1/2. And what we know from geometric series, well, if r is equal to 1/2 and that is less than 1, we know that it actually converges. So even though we can't prove divergence, we can prove convergence using a different test. So, just like we did today, I want to write out my explanation. Let me change colors so we can see the difference. I want to state the series. This is a specific series, so I want to use that name. So the geometric series with the absolute value of r equal to 1/2, which is less than 1, so those are my conditions, converges by the geometric series test. So get that down. If you have time, work on some of the practice. I know I've given you guys a lot of practice this week that we haven't gotten to, but really concentrate on the geometric series and the nth term test, just so you guys can get in the habit of the actual writing of the statements. Okay, so if you have any questions, come see me on Monday.